WhatsCracking is a PV module modeling app that predicts the probability of cell cracking for any module you can design. In this tutorial, we'll go through the complete functionality of the app. We'll design and build a new model, we'll run its simulation, and we'll analyze the results, both from the app's graphics window and from the available exportable files. We begin the process by selecting to start a new model. This activates all of our input design parameters. We begin by designating the size of the cell array by how many cells define the module's length and the module's width, and whether those cells are full-sized or fraction cells. You can see the default is a 6 by 12 full cell module. For this tutorial, let's change that to a half cell module, where we have 24 half cells in the length direction, but we keep the 6 full dimension cells in the width direction. You'll see that the absolute module dimensions are automatically updated every time we input a determining parameter. Next, we move on to the Module Geometry and Materials tab. Here we first have selections for the module construction and encapsulant type, then inputs for the thickness of every material in the laminate, and finally dimensions for module perimeters, margins, and cell spacing. By selecting the glass-glass module, our thicknesses defaults are automatically updated to 2 millimeters for the front glass and 2 millimeters for the back glass. Our choice for encapsulants are EVA, POE, and ionomer. For this tutorial, let's keep our construction at a glass backsheet module, which gives us the default of a 3.2 millimeter front glass and a 350 micron thick polymer backsheet. We'll leave our encapsulant type as EVA. Let's change the front thickness to just 3 millimeters. Let's do a full cell dimension of 210 millimeters. And let's increase our module perimeter to 20 millimeters. This is the distance between the edgemost cell and the edge of the glass. We need to add a module center margin for busing, since this is a half cell module. Let's make that 35 millimeters. And we'll keep the default cell-to-cell spacings of 2.5 millimeters for both the length and the width dimension. Our next design inputs are for framing and mounting. Under this tab, we can define 3 things: some details of the frame profile, the mounting location, and specifics about constraints at the mounting points. Let's change the height of our frame profile to just 45 millimeters, but we'll keep its depth at 35. And we'll define the mounting points as halfway between the module ends and its center. So this is a quarter of the module's overall length. You'll see in this figure below that we have automatically updated the total length of the module and the dimension of the mounting point with respect to the end of the module and the middle of the module. Next is the loading tab, which defines the simulation. Here we have a combo box to select the ultimate module load. This is a uniform load applied down to the front glass of the module. This will be solved in 100 Pascal increments up to the ultimate load selected. You can also choose the module temperature. This is a uniform temperature during the entire simulation. Let's select an ultimate load of the maximum 5400 pascals, and we'll keep the module temperature at 25C or 298 K. The last input parameter defines the cell strength distribution. We use a 2-parameter Weibull distribution with a characteristic strength of 97 megapascals and a modulus of 16. These default values are from an experimental study that is linked to in the description of this video. These are also likely liberal choices for these values and will result in early cell cracking. If you conducted your own strength characterization, you can enter your Weibull parameters here. However, your measurement should have been done on strung and tab cells to account for any residual stress and damage encountered through processing. Finally, the effective area is necessary for the probability calculation, and this default value should be accurate when your cell strength characterization was performed in 4-point flexure with an outer span of 80 millimeters and an inner span of 40 millimeters. Before we run our simulation, we can preview our module geometry by selecting this box. It typically takes a few seconds for the software to build and render our module. This rendering does not include the module framing or mounting points, and the wireframe type graphics just broadly illustrate the construction of the module. For instance, if we zoom in on the very edge of our module, we'll see domains that pertain to the top glass, the back sheet, but then separate sections for the top encapsulant, middle encapsulant, and the encapsulant associated for the layer where the cell exists, even though the cell does not come to the edge of the module. Those separate domains are separated in this rendering. Finally, if we're happy with our design and a quick inspection of module geometry is as expected, we can build and run our model with this selection. Depending on the size of the module, the ultimate load you've selected, and the speed and memory of your computer, the simulation may take up to a few hours to solve. This specific model has taken about an hour and a half to solve on my MacBook Pro laptop. The first plot to appear is the probability of cell fracture, solved for at the ultimate load of the simulation, 5,400 pascals. The color scale goes between a probability of 0 at green and 1 at the deepest red. So you can see that quite a few cells have 100% probability of failure. We can also select to plot cell stress and module deflection in this graphics window by first selecting the desired load and then the parameter to plot. So let's also see what cell stress looks like at the ultimate load of 5,400 pascals. We can again manipulate the plot any way we would like in 3 dimensions, as well as select these orthogonal axes to see 2-dimensional representations of the plot. And then we can switch to plot deflection, which renders the outer plane deflection of the module. And here we've turned on some exaggerated deformation. So you see the maximum deflection is just over 8 centimeters, but we've exaggerated that for the rendering. Now, any one of these plots can be saved by hitting that little camera button, choosing some specifics and where you would like it saved, and then that image will be saved to whatever folder you designate. And then finally, before moving on, I just want to illustrate how, again, we can choose any load in 100 Pascal increments of the simulation to see the result. So for instance, I've selected 2,000 Pascals, and now the plot comes up as mostly green, meaning the probability of any cell to fracture is very low, highest probability in the corners, looks like maybe 50%. Another thing you'll find is that after a model is solved, all the input parameters are locked, and I cannot change them because we've already solved that specific model, except for the Weibull strength distribution. I can change these values and update the solution, and the plot will accordingly update. So in case I want to get a sense that if I had stronger or weaker cells, how would that impact the calculation? So here I changed the characteristic strength from the 97 to 70 megapascals, updated the solution, and now I have at the lower load, I have quite a higher probability for more cells to fracture. Now finally, I can choose to export the module deflections. We get deflections along the module's length, and also deflections along the module's width. And we can export the probabilities of cell fracture. This one takes a second after you make the selection, because it has to run through and do all the integrations to calculate these probabilities. Now the last thing we'll do is take a look at these data exports, what the files look like, and how to plot them. Before we go over the specifics of the data exports, I thought it'd be helpful to go through some of our conventions. Now, since our modules are rectangles, we have quarter symmetry, which means we only need to be concerned about the results from 1/4 of the module, since they'll repeat themselves for the other 3/4. Now we have a column and row convention to designate cells, where columns go up and down. So this would be column 1, 2, 3, 4, and etc. And then the rows start at the center of the module and go up. So row 1, 2, 3. So for this 24 by 6 cell module, this outermost cell would be the 12th column in the 3rd row. The data exports for module deflection also take advantage of this quarter symmetry. So deflections along module width start at the center of the module and go towards its edges. And the module deflections for the module's length again start at the center of the module and go towards the module's end. This is the data export for out-of-plane deflection along the module's width. We have a couple headers here. First, we provide all of the modeling parameters, and they're in order from top to bottom as you entered them in that leftmost plane in the app. So if you recall, we started with designating the number of cells along the module's length, the fraction of those cells, the number of cells along the module's width, and so on. This is a great way to record the specifics of your module design, and then it's always connected to some results from that simulation. In the next header, in our left-handmost column, we have position along the module, again from its center to its edge, since we're dealing with out-of-plane deflection along the module's width. And then all the subsequent columns are those out-of-plane deflections at all of the loads solved for. So we start with 10 pascals, we go to 100 pascals, and then we have 100 pascal increments until the ultimate load of 5,400 pascals. This is the data export for probability of cell fracture. We again have the header that captures all of the modeling parameters for your module, and then for the results. Here, the leftmost column are all of the loads that the model was solved for. So in our case, from 10 to 5,400, again in 100 pascal increments. And then every column is the probability of fracture for a specific cell. And we go from column 1, row 1, all the way to that last cell in which would be in the 12th column in the third row, again taking advantage of the quarter symmetry of the module.